In this short video, we want to give you a quick recap of how to graph something in polar coordinates by hand, because you might have to do that from time to time. Show you where to find these things in the calculator, give you a chance to explore some of the basic polar curves on your own that you will see, and then maybe give you a shortcut for graphing these things a little bit faster that you may or may not use. So when you have no idea how to graph a polar curve, just like anything else, you're just going to plot points. And that's what I'm going to do here. We're going to graph the curve r equals 1 plus cosine of theta just by plotting points using values of theta that I know from the unit circle. Okay, this is a polar grid, and I've labeled points in the x and the y axis that correspond to the spokes that have the origin as their center, or the pole as their center. Each spoke is a half of a unit. Okay, and then these rays that pop out of the pole are each, I think, pi over 12. Okay, so this one would be pi over 6. This one would be pi over 4. This is going to be pi over 3. I'm not going to use pi over 6 or 5 pi 12s, but then we just go around the circle and fill in the rest. Okay, so just by using values of theta that we know, I'm going to start to plot some points here. When theta is 0, r is going to be 1 plus the cosine of 0, which is 2. When theta is pi over 6, I'm going to have 1 plus the square root of 3 over 2. And I'll just write this down because I'll probably use it a few times here. The square root of 3 over 2 is roughly 0.85. So on this ray right here, I want to go 1.85 units from the origin, which is roughly there. When theta is pi over 4, I have 1 plus the square root of 2 over 2, and the square root of 2 over 2 is roughly 0.7. So I'm going to go 1.7 units, which is a little bit closer than the last one, but I'll put it right here. Okay, then we have pi over 3. We're going to have 1.5 exactly. So 1.5 puts me here. And then pi over 2 gives me 1 plus cosine of pi over 2, which is just 1. Okay, so there I have graphed just the first quadrant points for this polar curve. I'll try to connect them best I can with this slate that I have here. Okay, so that's okay. It's not great. We'll take a look at a better picture of what this looks like on the calculator shortly here. All right, let's continue. We now go to 2 pi over 3. Cosine of 2 pi over 3 is negative square root of 3 over 2, or sorry, negative 1/2. So now I have 1 minus 1/2, which gives me 1/2 for this ray right here. So that's down here. Now we go to 3 pi fourths. So I now have 1 minus 0.7. So that's 0.3. You can see we're getting closer and closer to the pole here. And then we go to 2 pi thirds. I'm going to have 1 minus 0.85, 0.15. So again, very close. And then we get back to pi. We have 1 minus 1, which puts me back at the pole. Okay. We're going to see a little bit later that points where r equals 0 are going to be very important for us to help us graph quickly. Okay, so this graph spirals in towards the pole and gets to the pole when theta is pi. All right, now let's see what happens in quadrant 3 angles. You're going to have the same values pop out here. So 7 pi over 6 will give us 1 minus 0.85 or 0.15. And then we'll get 1 minus 0.7, so 0.3. And then 1 minus 1/2, which is 1/2. And then when we get back to 3 pi over 2, 1 minus the cosine of 3 pi over 2 puts us back to 1. Okay, and you're starting to see some symmetry happen here. And that's because cosine's negative in quadrant 2 and quadrant 3, and you can guess that what you're going to see in quadrant 4 is the same thing you saw in quadrant 1, and that is accurate. Okay, so I'll just quickly plot those dots best I can here. So where are we going next? We're going to 4 pi thirds, which gives us to 1.5, and then 1.7, and then 1.85, and then back to 2. Okay, so there's our picture, just using points that we know from the unit circle. Okay, so let's take a look at our calculators, because a lot of these problems you will have the calculator for, not all of them. But let's compare what we drew with what we actually would get using a graphing utility. So first of all, how do I get a polar graph? I'm going to go to Menu, we're going to choose Graph Type, and then we're going to choose Polar, just like we chose Parametric before. Alright, here you have R1 of theta, just like F1 of x used to be the label. Here you'll type in your function. You see down below, it gives you the bounds for the value of theta, the dependent variable. Here you have 0 to roughly 2 pi, and that's fine for most graphs. So we have 1 plus the cosine of, and then I think theta is down here in the pi menu. There it is. Alright, and there you have a picture. If I zoom in a little bit, it will look exactly, not exactly, but pretty close to what we drew. But you can see the 0.20 and it goes to the pole when theta was pi. So a pretty good picture. Notice that if we change how much theta can be, you will only see a portion of the graph. Try that again. There. Okay, here you only see half the graph because we stopped the value of theta. And it's going to be important to know in the future how much of theta do you need to get the entire graph. In this case, you needed to go 0 to 2 pi for that to happen. Okay, I would encourage you to pause the video at this point and mess around with these families of polar curves so you can get a feel for the common guys that will pop up. We've divided them into 3 packets. Okay, so these graphs will all have something in common here, this first column. You want to notice what the value of the coefficient does to the graphs and whether or not that's positive or negative. These 6 are going to have something in common, and again you want to pay attention to what the values of the constant and then the coefficient do to the graph. And then these 6 have something in common as well. These are the 3 big families that pop up in the calculus of polar curves as far as area and derivatives and graphing. So I would encourage you to take a look at those. And let's end up with maybe finding a way to plot this a little bit faster than by plotting points. Okay? So what I first want to point you to is when is the R equal to 0? That tells you when your graph returns to the pole. Okay, so what happens, or what's good to have access to, is a sign chart for your polar function. And I'm going to go ahead and just assume that 0 to 2 pi is going to be enough data. In this case it is. Sometimes that's too much data. Sometimes it's not enough. But let's go with it here. So 0 to 2 pi are my bounds. And now I'd like to know when is this equal to 0 between 0 and 2 pi. Well, cosine is equal to 0 when the input is either pi over 2 or 3 pi over 2. So when 2 theta is equal to pi over 2, or when 2 theta is equal to 3 pi over 2. Okay, those are my key guys. And so if I was just solving this for one period, I'd say that the answer is going to be pi over 4. Okay, and the other answers would be pi units away because the period of cosine 2 theta is going to be pi. So if we had another pi k, we'll get more solutions. We'll talk about how many we need. Same thing happens here. My theta would be 3 pi over 4 plus pi k. Now how many of those solutions live between 0 and 2 pi? Okay, well we definitely need pi over 4. We definitely need 3 pi over 4. Now what's the next solution that would occur? Okay, well if I take pi over 4 and add pi, that puts me at 5 pi over 4. So I need 5 pi over 4 on my sign chart. And if I add pi to 3 pi over 4, so I'll have 7 pi over 4. So that concludes the list of zeros that occur in one period or in one cycle of the unit circle, 0 to pi. Okay, from now you want to fill in the signs, and I'm going to go ahead and save us the effort of actually doing that, but it ends up being plus, minus, plus, minus, plus. Okay, now what this does for me is two things. It tells me when the graph returns to the pole, which is useful, and it also tells me when the r, this displacement, comes out to be a positive versus a negative. So that'll tell me when my dots are actually plotted along the value of theta that I am inputting versus reflected back to a different quadrant. Okay, so let's take a look here. When theta is 0, we plug in 0 into this function, we'll get an r value of 1. Okay, and again, I'm going to say that each of these spokes is a half of a unit. Okay, so this is 1, and this is 1, and this is 1, negative 1 actually, and this is 1 here. Okay, now what happens here is between 0 and pi over 4. Okay, pi over 4 is this red ray right here. My r values are positive, right? But at pi over 4, I return to the pole. So that means that between theta 0 and pi over 4, I will be still in this quadrant, but I will return to the pole when theta is pi over 4. Okay, so without knowing much of anything else, I'm going to say that the graph starts to do something like this. It starts to spiral in towards the pole, and it gets there when theta is pi over 4. Okay, between pi over 4 and 3 pi over 4, so that's between here and way over here. Okay, between those values of theta, my r is a negative, which means the dots don't get plotted here. They get plotted in quadrant 3 for this portion, and then in quadrant 4 for this portion. And then when we get to 3 pi over 4, we return to the pole. Okay, so if you can imagine what's happening here, there would be dots normally somewhere in this ray, this ray, this ray, and this ray, but they're going to get reflected down here. So let's take a look at where we would be at pi over 2, and that'll give us an idea of where we're going to end up at pi over 2, and then we'll continue on. The cosine of pi over 2 times 2 would be negative 1. So these values get reflected in the quadrant 3, and we end up at negative 1 when theta is pi over 2. All right? And then when you're in quadrant 3, when you're quadrant 2, between pi over 2 and 3 pi over 4, your values are going to get reflected back into quadrant 4. Remember, at 3 pi over 4, we have to be back at the pole. So your graph's going to start to spiral in towards the pole. Okay, now we're back to positive r values between 3 pi over 4, okay, which is here, and down here, 5 pi over 4. You're going to have positive r values that eventually will spiral back to be back at the pole. And again, it's good to know where you are, I guess, at the four corners, so to speak. So where would you be when theta is pi? When theta is pi, you'd have cosine of 2 pi, which is going to be 1. And if you are going in the direction of pi, that would place you right here at the rectangular coordinate negative 1, 0. Okay? So with positive r values, I'll be here. Still have positive r values, but now they're going to start to spiral back in, and that puts me back at the pole. Now, between 5 pi over 4 and 7 pi over 4, my r values are now negative. Okay? So instead of being plotted in quadrants 3 and 4, they get reflected to be in quadrants 1 and 2. Let's take a look at where we're going to be when theta is 3 pi over 2. When theta is 3 pi over 2, you're going to have the cosine of 2 times 3 pi over 2, which is the cosine of 3 pi, which is negative 1. And if I'm supposed to be along this ray, and my r is negative 1, it puts me back up here at 0, negative 1 in rectangular coordinates. So what that means is I have negative r values. I end up here, and then I need to spiral back in towards the pole. Okay. Obviously, my graph should be more symmetric to that. And then finally, we end up with some positive r values between 7 pi over 4 and 2 pi. And if I'm 2 pi, then I should end up at 1, 0, 1. as far as rectangular coordinates, but a r value of 1 when theta is 2 pi. Okay, and so this is the rose curve that you might remember from last year with 4 petals. And the important thing to see there was how it was plotted, okay, because that's going to be important for determining area and other things of that nature. So this got plotted going starting at 1, 0 in rectangular coordinates, heading to the pole, and then coming down here for this petal, and then coming up here for this petal, and then out here for this petal, and then finishing up right here. Let me trace that out again with the highlighter in case I miswrote there. But we started off here, and then we came down through here, which was my values between pi over 4 and 3 pi over 4. Then between 3 pi over 4 and 5 pi over 4, I needed positive r values, so that was this petal here. And then we were between 5 pi over 4 and 7 pi over 4, I had negative r values, which placed me up here for that petal. And then we finished with positive r values, which brought me back to my starting point here. Okay, so in case I traced it out incorrectly just a second ago, I just highlighted it for you to make it more clear. Let's double check with the calculator to see that that's the accurate picture. So we have, once again, in menu, going to polar for graph type, and I want the cosine of 2 theta. And let me zoom in a little bit because that's not very descriptive. Oops, center. Let's try that again here. Menu, zoom standard, and then zoom box. That's what I meant to type there. There we go. So there's our four-petaled rose curve. Now, hopefully that helps out a little bit. You're not going to have to graph a ton of these by hand, but on the same multiple choice question where they ask you about area of one of these graphs, or even on a free response question where you don't have the calculator, you're going to have to know how to graph it, what it basically looks like, and then maybe where and when one of these petals gets filled in. Because you might be asked to find, for example, the area of one of those petals. And you need to know when one begins getting graphed and when it gets enclosed. So we'll see you in class to practice the calculus involved with polar functions. Hopefully this was helpful.